So the next topic, we're going to have a look at the difference between some different types of acids. So some acids only have the capability of giving away one H plus, because that's all they have to give, but others have actually 2 or 3 H pluses that are possible that they can give away. So the ones that only have a single H plus is something called a monoprotic acid. So that means that these monoprotic acids have one H plus to give away, and to do that they'll have to react with a base in just a single acid-base reaction. So we've seen an example of a monoprotic acid already today, and that was our hydrochloric acid. So based on this representation of HCl, we can see that the HCl actually has the capability of giving away one H plus. So within HCl we can have the separation into these two ions where the H plus and Cl minus can actually separate. So because the HCl only contains the capability of producing one H plus, this would mean it's a monoprotic acid. So the mono meaning one, and it's got that one H plus to donate. So you can see in the course of this reaction, the H plus will be donated from the HCl to H2O, and after doing that, HCl has become Cl minus. So the Cl minus has no more H plus to give away. Therefore, we can class the original HCl as a monoprotic, meaning it has that one H plus to give away to a base. What about something like a diprotic acid? So di meaning two, it's actually got two H plus, which can be given away via acid-base reactions. But the key here is that each time the base gives away an H plus, it actually needs a separate acid-base reaction. So in theory, to give away both of its H plus, the diprotic acid will need to give away a single H plus in two separate acid-base reactions. So the example of the diprotic acid we have here is carbonic acid, H2CO3. So in the first acid-base reaction that the diprotic acid will be involved in, we'll have H2CO3 donating one H plus to water, and you can see that that has now produced products that have either one more or one less H plus. So even when the acid is converted into the conjugate base in this case, it actually still has the capability of behaving like an acid in another acid-base reaction. And that is because it still has another H plus. So that hydrogen within HCO3O minus can actually be lost as an H plus. And that's what we see in the second acid-base reaction here. So that HC3O minus, which was produced in the previous acid-base reaction, can actually function as an acid again to give away its second proton. And by doing that, it then becomes CO3 2 minus, now that has no more H plus to give away. So even though the H2CO3 has the 2H plus to give away, how many acid-base reactions does it require to do this? So each acid-base reaction only results in one H plus being given away. So for H2CO3 to give away both of its H plus, it needs two separate acid-base reactions. So if you look at the structure of H2CO3, essentially both of those hydrogens can be lost as H plus in acid-base reactions. But when this happens, the extra electron is actually retained by the product component of the acid-base reaction, hence why the HCO3 minus and the CO3 2 minus retain that negative charge, because the electrons within these hydrogen atoms are being retained, but the H plus are being removed. So there's a little bit of extra information there. Takeaway message from this slide is that diprotic acids have two H plus that can be given away in an acid-base reaction, but each reaction only gives away one H plus. So that means we need two separate acid-base reactions to allow H2CO3 to give away both of its H plus. And there is a third type of these acids. We now have these triprotic acids. So tri meaning three. So these ones actually have three H plus that they can possibly give away. So how many acid-base reactions do you think a triprotic acid would need to give away its 3H+? Well, it actually needs 3 separate acid-base reactions, and we can track how this happens with our H3PO4 triprotic acid in the example down the bottom here. So in each acid-base reaction shown here, we have the acid losing 1H+. So initially, the H3PO4 gives away the 1H+ to H2O, becoming H2PO4-. So that H2PO4- can then behave as an acid in the next acid-base reaction, giving away another H+. And in doing so, the acid becomes HPO4-2-, still capable of giving away another H+ because it still retains that hydrogen. So we can have a third acid-base reaction where the HPO4-2- gives away an H+ to H2O, and by doing this, it's now given away all of its H+. So notice that the final product here that the HPO4-2- turns into no longer has any hydrogen attached. So therefore, it's now incapable of giving away any more H+. But you can see that the H3PO4 here, by undergoing 3 different acid-base reactions, has actually eventually become PO4-3-. Okay, so to do this, it gave away 3H+, and it required 3 different acid-base reactions. So to summarize this section, essentially, whether it's mono, di, or tri, for the acids here, it tells you how many H+ that particular acid or type of acid is able to give away. So if it's monoprotic, it can give away a single H+ in one acid-base reaction. If it's diprotic, then it has 2 H+ to give away, and it needs to give these away via 2 separate acid-base reactions. And then the third example was our triprotic acid that had 3 H+ to give away, and each of these needed to be given away in a separate acid-base reaction. So in total, it requires 3 acid-base reactions to give away all of its H+. Alright, so we've covered the content now for the first 4 questions. So remember, you can access these via the revision quizzes on the LMS. So under the weekly tab for this session, you'll be able to find the revision quiz. So please pause the lecture now and have a go at these questions to confirm your understanding of what we've been through so far. So to summarize this section, we saw that acids were the components within an acid-base reaction that are donating H+. So H+ is being removed from the acid and given away. And the bases are the components that are accepting those H+ that are being given away by the acid. So we've got this relationship where the acids and bases are working together. The acid's giving away the H+, being accepted by the bases. And in doing so, it actually changes both the acid and the base through the process of the chemical reaction. So during the acid-base reaction, once the acid has donated its H+, that actually means the acid has now lost an H+, and that actually means it's become what we call a conjugate base, or product base. Whereas the base, through taking part in an acid-base reaction, is accepting an H+, and by doing this, it actually has more H+ than it had to begin with. So it actually becomes a product that we call the conjugate acid, because in theory, it has the capability of giving away that H+ that it just accepted in another acid-base reaction. So to work out whether a component is acting as an acid or a base, essentially it's just that method of pairing your reactants with your products and making sure you have the pairs that differ by 1 H+, and then working out whether to go from the reactant to the product, the reactant has lost or gained H+. So we saw that each acid-base reaction has 2 conjugate acid-base pairs. So we got those pairs from working out which reactant matched to which product, and there were 2 of these pairs. And the difference between each of the components within that one pair is going to be 1 H+. And the most recent thing we saw was the difference between our mono, di, and triprotic acids. So the monoprotic acids had the ability to give away 1 H+, diprotic could give away 2 H+ in 2 different acid-base reactions, and the triprotic actually had 3 H plus to give away to 3 bases within 3 separate acid-base reactions. Alright, so we're going to have a look at the strength of acids and bases now. So I'm sure you've all heard of very strong acids like hydrochloric acid or sulfuric acid that actually can be quite dangerous. So we're going to show you in this section what the difference between a strong acid is and a weak acid and how you can determine which one's which. Okay, so a strong acid is basically an acid that really wants to be like an acid. It really wants to donate its H plus to a base. So this means that it's very reactive. Okay, so essentially the strong acid will do whatever it can to get rid of its H plus. And this comes back to the fact that the strong acid is extremely reactive and unstable. Remember, whether it's an atom or a compound, they want to do whatever they can to be stable. So because the strong acid is so reactive, by giving away its H plus in an acid-base reaction, it actually allows it to become more stable. So that's what we see here. The strong acid wants to give away H plus to become more stable. So how can it do this? It can do this by being part of an acid-base reaction. So after giving away its H plus, the strong acid will actually be converted into a conjugate base, because once it loses that H plus, it's no longer going to have the capability of giving away the H plus. So we call it now a conjugate base. And because the strong acid really wants to get rid of the H plus, essentially what this means is that all of the strong acid compounds will all give away the H plus. So we can say that 100% of the strong acid will give away its H plus. This corresponds to a non-reversible reaction. So a reaction that only proceeds in one direction that we show as a single arrow. So the majority of the reactions I've shown you so far actually follow this pattern where it was just a single direction arrow. But I'll show you some other ones where this is not the case for weak acids. So here's the example of our strong acid where all of the HCl strong acids will give away their H plus to the H2O, and therefore we can define HCl as a strong acid. Also notice that it's a single direction arrow. So all of the reactants are being converted to all of the product compounds on the right hand side here. So when we draw a chemical reaction like this, it looks like there's just one HCl and one H2O, but in reality there's likely to be heaps and heaps of these different components. And because it's a strong acid, all of the strong acid compounds will be giving away the H plus. So to sum up what we've seen on this slide, strong acids are really good at giving away their H plus because they're very reactive. And once they give away their H plus, they'll actually become more stable. And in that form, they'll then be the product, which is the conjugate base. What about the weak acid though? What are some of its characteristics? Well, the weak acid is actually not very good at being an acid in terms of the fact that it only very occasionally is going to donate its H plus. Remember, the strong acid always donated its H plus. So this is the main difference between a strong and a weak acid. Strong acids give away all their H plus all the time, as long as there's a base to give it to, whereas the weak acids will only occasionally donate their H plus. And this is because the weak acid is actually already stable and unreactive. So why would it want to change? It doesn't really. So we can say that the weak acid doesn't want to give away its H plus because it's already stable. But occasionally the weak acid will lose its H plus around 5% of the time. So when the weak acid does give away its H plus, it becomes a conjugate base, which is actually a bit less stable than the initial weak acid is. So remember, atoms and compounds always want to be stable, so that actually makes this reaction where the weak acid is giving away its H plus less favorable, because the weak acid actually becomes a product that is less stable than the initial weak acid was. So a good way to pick out where you have a weak acid is the fact that the reaction will be shown as a reversible one. So you're going to have that double-headed arrow indicating that the reaction can go in either direction. In terms of the weak acid being converted into the form where it's giving away its H+, this will happen about 5% of the time. So if we go back to the previous slide, we saw that the strong acid, those compounds gave away their H+ 100% of the time. So they were really good at giving away H+. Compare this to the weak acid, only 5% of the time does the weak acid give away its H+. So in that way, you can think of the weak acid as being not very good at being an acid. It would rather hang on to the H+. So here we can see an example of the weak acid where we've got the carbonic acid, H2CO3, reacting with water to create our compounds on the right hand side here. So in this, if the reaction was going from left to right, we would have the H+ being donated from the weak acid to the water. But notice now that we've also got a reversible arrow here, which tells you that the products can actually be converted back into the reactants in this case. And that direction of the reaction would actually be favored because only 5% of the time does the weak acid give away its H+. So more often the reaction will actually be going from right to left. But don't worry too much about this. Main takeaways from this is that weak acids are stable and don't want to give away their H+. However, they will occasionally give away their H+, about 5% of the time, becoming less stable. Alright, so let's compare some of these properties of our strong and weak acids. So we know now that the strong acids readily donate their H+. So they really want to get rid of their H+ because they are unstable and they want to become more stable. So once the strong acid is able to give away its H+ to a base, it's then able to become the more stable conjugate base. So in this case, the strong HCl acid will give away all of its H+ to H2O, indicated that 100% of the HCl will give away their H+ here, and then the HCl will become the conjugate base, which is Cl- here. So that conjugate base, will that be more reactive or less reactive than the initial strong acid? It'll be less reactive, which corresponds to being more stable. So essentially what this means is that strong acids will do whatever they can to react and get rid of their H+. And this is actually what makes strong acids really dangerous. They'll basically react with any organic material to give away their H+ and force the water molecules within that organic material to actually be converted into the conjugate acid here, H3O+. What about a weak acid? How does that compare? Well, we know that the weak acids only occasionally are going to donate their H+, and this is because the weak acid compound is actually already very stable and unreactive. So you can think of it as being the weak acid not wanting to give away its H+. Why would it? It's already stable. So essentially, we see a reaction here for the weak acid where H2CO3 about 5% of the time will give away its H+ to H2O. But notice now that it's a reversible reaction, so some of the time we'll actually have the products being converted back into the reactants as well. So what do you think are the main differences between a strong acid and a weak acid? Well, it all comes back down to how good each of them are at giving away H+, which remember is the function of an acid, to give away H+ to a base in an acid-base reaction. So which of the strong and weak acid are best at giving away H+? Well, the strong acids are much better at giving away H+. 100% of the strong acid compounds will donate their H+. Whereas the weak acid, are they good at giving away H+? Not really. Only 5% of the weak acid compounds will give away the H+. So where does this difference come from? Why are the strong acids so much more willing to give away their H+ than the weak acids are? It comes back to stability. The strong acids are really reactive and therefore want to become more stable by giving away their H+. And once they've done that, they'll become a more stable conjugate base. What about the weak acids though? Do they become more stable by giving away H+? No, The weak acids are actually more stable if they hold on to their H+. So this is their preference. Roughly 95% of the time, the weak acids won't donate their H+, so they'll retain their H+, and be more stable.